Okay, so I'm going to talk about lattices in cryptography, and it's really a huge topic, which is really hard to cover within 1 hour. And I decided to cover only one part of the usage of lattices in crypto, essentially the part related to constructions of cryptographic primitives, encryption schemes, and different bizarre cryptographic objects. But there is also another part which is dedicated to cryptanalysis, to the cryptanalysis of schemes based on lattices, or even to schemes which are not based on lattices, based on more classical problems as the problem of factoring, for example. I'm not going to cover this part, but I guess in the Asia Pacific part of the summer school, there was a talk about cryptanalysis and reduction algorithms. So please check it when it's going to be available on YouTube. So, okay, thank you to Philippe for his talk yesterday, because he essentially introduced almost everything regarding basic definitions related to lattices. I will do a very quick recap. So Euclidean lattice is a discrete additive subgroup of the Euclidean space, and it's defined by some matrix B of dimension n times k. And we assume that k is smaller than n, and essentially that the columns of this matrix B define a basis of the lattice. So we assume that this matrix B is of full rank, meaning that the rank of this matrix is k and the dimension is n. So we can also represent it in a geometric way as the set of points which are sort of nicely arranged in the space along certain families of parallel lines. We also have the following definition of a geolattice, which is quite important for us for the future discussion. The geolattice is defined with relation to the inner product in the Euclidean space. And also we have the minimum distance, which is essentially the length of the shortest non-zero vector in the lattice. So lattices, as Philippe demonstrated yesterday, are often affiliated with a certain tiling of the space. So here you can see the picture of Maurice Escher, which is called number 105 or Pegasus. And essentially this tiling represents a pretty standard two-dimensional integer lattice. So we put points on i's of those Pegasi, then we get a lattice. And what is nice here, you can see also that the fundamental region is not some abstract geometric shape, it's essentially a Pegasus. So, okay, having geometric representation of a lattice, we can define pretty simple problems which are surprisingly hard to answer. For example, a boundary distance decoding problem, where we put a random point in the space, and we guarantee that this point is close enough to a certain lattice point. So essentially, it's located in some proximity of a certain unique lattice point. And the goal of bounded distance decoding problem is to find that specific lattice point. Essentially, if we have the target point depicted in red, we want to find the lattice point here. This problem is known to be NP-complete if the parameter gamma here, essentially parameter estimating the proximity, is bigger than 1 over square root of 2. Oh, sorry, is smaller than square root of 2. We also have the shortest vector problem, which essentially asks to find the shortest vector given a certain basis of the lattice. And of course, we can give a pretty good basis, nice basis, as Philip put it yesterday. But usually we're given a certain bad or ugly basis, and we need to find the shortest vector there. So this problem is also known to be NP-complete if we want to find like really the shortest vector. We can also relux this problem. And essentially, instead of asking about the shortest vector, we can ask about the some short vector within a certain radius defined by gamma and the minimum distance. And for constant gamma, this problem is also known to be NP incomplete, NP hard. Okay. So of course, the approximate SVP is simpler just because we have several such short vectors than in the exact SVP. We also have a decision version of SVP called gap SVP. We're given a basis of the lattice, and the goal is to return yes if the minimum distance of this lattice is smaller than some parameter d, and no if the minimum distance is larger than gamma d. And again, this problem is also known to be NP complete as long as gamma is constant and doesn't depend on the dimension of the lattice. We also have generalization of shortest vector problem, where we are asked to find several independent vectors, or maybe another basis of the lattice. Given an ugly basis, the problem asks to find several short independent vectors. Okay. So why lattices are useful in crypto? First of all, they are super simple, so we can implement them only using very standard matrix vector arithmetic. And due to that, we have also pretty fast algorithms, and running time efficiency is even better than for classical crypto systems based on elliptic cryptography or systems based on factoring, such as RSA. There's no efficient quantum algorithm so far that can solve hard lattice problems that I've mentioned. And also we have pretty nice property of lattice-based crypto, namely that in order to attack a crypto system based on lattices, we need to solve all the instances of certain classical problems on lattices. And this so-called security reduction is called worst case hardness. And also lattices provide super versatile functionality. Essentially, we can build very exotic, very strange crypto systems with very nice properties. And for example, for certain families of cryptographic algorithms, we only know that they are possible based on lattices. Okay, let's start with the first problem, which was applied in cryptography, and which has a pretty nice connection to lattices. This problem is called short integer solution, or CIS for short. So in this problem, we are asked to solve a system of linear equations where aij's are uniformly random integers modulo q, and si's are essentially unknowns in this system. So if si's are not bounded, if they're not short, then we can easily solve this problem using Gaussian elimination. But if S is short, then problem becomes pretty hard, and we can actually prove this hardness. So essentially, CIS can be reformulated as a lattice problem in the following way. So we can define a lattice LA, which essentially has all the integer vectors living in the kernel of linear transformation defined by A modulo Q. This lattice is kind of similar to the geo lattice, but not quite. And essentially, what we need to solve, we need to find a short vector in this lattice, which means that we need to solve approximate SVP problem. So using CIS, we can define the following cryptographic function, iTies one-way function. It's super easy. Essentially, we take a matrix A and we multiply it by a binary vector X, which is the input of this function. And in order to find collisions of this function, we need to solve a CIS problem. Because if we have a collision, then we have two vectors X and Y, which essentially are mapped to the same value. And then just, we get this expression where A is multiplied by X minus Y. And this is essentially the SIS problem because the coefficients of x minus y are small, they are ternary. And in 1996, ITI proved that if we have large enough M, meaning that we have enough enough columns of the matrix A, then finding collisions of F is at least as hard as gap SVP and approximate SIVP, two problems, for any n-dimensional lattice. So this is worst case hardness result. But the problem is that this function is not that efficient because in order to compute this function, we need first of all to keep the matrix A, and it's pretty huge. It contains M and elements from of integers modulo Q, and we also need to perform M and operations. So due to the hardness result, we have a certain dependency on the dimension of the lattice n squared. And we can essentially mitigate this by constructing matrix A in the following structured way. So essentially, we split A into square chunks, and then each chunk is essentially is anti-circulant matrix, which is defined by the first column. Then it's shifted in the next column, but the values which kind of went off the range, they negated. So you can, of course, understand that these matrices essentially represent the matrix of multiplication by polynomial defined by the first column, modulo x to the n plus 1. In this way, we can redefine SIS as not the matrix vector multiplication, but the inner product of vectors containing values from this polynomial ring. And more generally, we can replace x to the n plus 1 by some irreducible polynomial. Here also x to the n plus 1 meant that this polynomial was 2nth power secatomic, so n is a power of 2. And in 2006, Lubashevsky and Michancho proved that finding collisions for this function is at least as hard as approximate SVT for any ideal lattice. I will later tell you what ideal lattice is, but I think if you watch the talk of Alexander or Philippe, they also introduced these notions. It's easy to see that ring SIS is more efficient than just standard SIS because we perform less operations. We can use fast Fourier transform in order to multiply elements. And also, we need to keep much less values. Essentially, we need to keep m over n polynomials. Each of those contains n coefficients, which are integers modulo Q. So as I said, we can define, using SIS, we can define one-way functions, and we can define also collision-resistant hash functions. And it's not that hard to see that from collision-resistant hash functions, we can define signatures, which was done for SIS as well. Can we do more? Can we do more interesting stuff using lattices? Yes, we can. And essentially, if we base the security of our system on LWE, learning with errors problem, then we can do a lot of interesting things. So some of you may know about this pretty standard statistical tool called linear regression, where essentially the problem is to find certain linear model which approximates nicely the given data. So it can be defined using matrices. We have some output of our experiment. We have the matrix containing all the input values, and each column corresponds to a certain parameter of an experiment. And then we need to find these secret parameters, which essentially correspond to certain influence of input parameters of the experiment. And we also need to take into account that during experiments, we can have some noise. linear regression can be easily solved if this matrix X is nice enough by linear least squares method or something else. Mainly because all the elements of these vectors and matrices, they're contained in the field of rational numbers. But what if we work over the ring? So we can define also linear system with noise over the ring, where these matrix A, the elements of this matrix A are sampled uniformly random. We have unknowns as i's, and we have some noise, which must be small. So essentially, we have two versions of this problem of search LWE. The first one is search LWE. We are given the vector B and the matrix A, and we need to find a known vector S. And we have the decision LWE, where we need to distinguish the pair B and A from uniformly random pair of a vector and a matrix. And surprisingly, these two problems are equivalent. So it's pretty easy to see that decision LWE is, if you can solve search LWE, then you can easily solve decision LWE because you found S and you kind of established the fact that the sample you are given was created using LWE. But also, if you can solve decision LWE, you can recover S, which is not that evident. So if LWE has no noise, then the problem is easy, as it was for cis, and we can again use Gaussian elimination to solve the problem. But otherwise, this problem might be hard, and Gaussian elimination will only amplify errors, essentially this error here, which doesn't allow us to recover S eventually. So what is the relation of LWE to lattices? We can represent any LWE sample as an instance of bounded distance decoding problem, namely given the vector B and guarantee that the noise E is small. We know that there exists a unique lattice point, depicted here in red, which belongs to this lattice defined by A, which is also here. And essentially, by finding this point, we can then use Gaussian elimination to recover S. Also, we can look at LWE as an SVP instance. So we can use what's called Cannon's embedding in order to create this lattice B, which is essentially consists of matrix A, vector B, and some integer t. So this integer t, if it's larger than the distance between our target vector B and the lattice defined by A, then in the lattice defined by B, we have this unique shortest vector. And the goal is to recover this unique shortest vector. If we go to the other direction, then the hardness of LWE is defined in the following way. So decision LWE with the error distribution, which is Gaussian or discrete Gaussian with standard deviation larger than 2 times square root of n, where n is the dimension of the lattice, is at least as hard as gap SVP and SAVP using quantum computers. Or it's at least as hard as gap SVP using just classical computers. In practice, in order to create crypto out of a hard problem, we need to prove the semantic security of a scheme. And essentially, we need to prove that the encrypted messages of our scheme are uniformly random. This is essentially very similar to the decision LWE problem. So we can reduce the hardness of our crypto problem to decision LWE. And then we can go to search LWE, as I explained. And from search LWE, we have hardness for gap SVP and SIVP. So in this way, we can base the security of our crypto system on some hard problems based on lattices. So just give you a sense of how we can build an encryption scheme from LWE. Let's consider this very simple public key encryption scheme. So we have our two usual suspects, Alice and Bob. Alice has a secret key S, and she generates an LWE sample, which becomes a public key. So Bob then generates a random binary vector X, and he computes the vector A prime and an integer B prime, where in the most significant bit of B prime, Bob puts his message bit. So you can see already here that in order to recover the secret, the adversary should solve a LWE problem because he is only given AB. So then Bob sends his encryption, A prime, B prime, and computing this expression, Alice can easily recover the message. So here rounding essentially corresponds to the fact that to have some noise here, which will be scaled by 2 over Q, and then removed by rounding because it won't be an integer. It will be something much smaller than Q over 2. And it was proven by Regev that in order to distinguish A prime and B prime from some uniformly random pair, one should, if somebody can distinguish A prime and B prime, then he or she can solve a decision LWE problem. So as explained, LWE can be used for the design of public key encryption schemes, also for signatures. So for those of you who don't know what the cryptographic signature is, it's essentially some data attached to some document, some file, which can be verified, which can be also undeniable, which can also be forged. But also, this is pretty standard stuff, but LWE can provide also very nice functionality. For example, using LWE, we can compute identity-based encryption, where instead of using some abstract public key, we can just take Alice's ID and use it as a public key. We can also build oblivious transfer, where Alice sends 1 out of n values on Bob's request, but Alice doesn't know which value she sends to Bob. And Bob also doesn't know other n-1 values. Also, we can build non-interactive zero-knowledge proofs, where Alice proves to Bob that she knows some little secret about Bob, but she doesn't want to reveal each one. Fully homomorphic encryption, where Bob can compute on data encrypted by Alice without her secret key, which is kind of counterintuitive, but it's possible. And also attribute-based encryption, where only users that have right credentials or attributes can decrypt ciphertext with related attributes or credentials. This is pretty important if we want to organize a certain policy within a big company or big organization in order to prevent non-authorized access to certain data files. What is very nice about LWE is that fully homomorphic encryption and attribute-based encryption is only known to be based on LWE so far. We don't know any other primitives which allow us to do this fancy functionality.
So yeah, we have one question about decryption failures.
Mm-hmm.
So Bruno Sterner is asking whether decryption failure can be due to the rounding procedure you describe in the decryption phase.
Of course, yes, it can be. So essentially, if E here is big enough, then of course it can happen. In the encryption schemes, it's it's quite critical because people try to optimize parameters such that I mean, the size of this E is really close to the edge where decryption errors become apparent. But of course, I mean, when people construct encryption schemes, then yeah, they take this into account. Does it answer the question?
I think so.
No.
Thanks.
Okay. So as you noticed, LWE has a pretty similar structure to the original CIS. So maybe we can optimize LWE in the same way as CIS. So essentially, we can introduce some ring structure and do LWE faster. So again, as for CIS, let's identify the vector space of integers modulo Q with a polynomial ring defined by some polynomial f and some integer Q. So this f is irreducible and monic. So we can see every polynomial of this polynomial ring as the vector of its coefficients. Then the product in this ring can be represented in the matrix notation in the following way. So essentially, we can represent the multiplication of A and S as the matrix vector multiplication, where A sub I is the matrix of multiplication by the polynomial AX. So instead of storing the entire matrix A containing n times k elements or n times m elements, we can sort just n integers corresponding to the vector coefficients of A. The same example as before, if f is x to the n plus 1, then we have anti-circulant matrix. But in general, if we have any reducible monic polynomial f, then then the matrix A sub A is essentially represented by A, and then x times A modulo f, and so on. So in this way, we can define ring-based analog of LWE, where essentially instead of having matrix A, we have A sub A. And in order to have some security, because we know that LWE is secure if this noise is sampled from Gauss distribution, where each coordinate is sampled independently. So essentially, we have this ring-based LWE example. But the problem is that this is not ring LWE because we can't prove a general statement about the security of this system. We only know that the problem of recovering S here is hard as a ring LWE for some families of defining polynomial f of x. For example, for cyclotomic f, we have such correspondence. And this problem is often confused with ring LWE, but in fact, it's called polynomial LWE. So what is ring LWE then? Let's again redefine things which have been already defined in the previous talks. So we have K, the number field defined by some polynomial f, and K has only n complex embeddings. So in fact, some of them might be real. And these complex embeddings define the canonical or Minkowski embedding of the number field. And what is nice is that the image of K under the canonical embedding is isomorphic to the Euclidean space with relation to the Hermitian inner product. It means that we can define geometry on this space and we can define lattices. So let's take the ring of integers of K, and for any ideal I of the ring of integers, the image of I in the canonical embedding will be an ideal lattice. We can also define the dual ideal with relation to the trace of the number field. And the image of the dual ideal will be also a lattice. And here you can see the relation of the lattice defined by the dual ideal and the dual lattice of an ideal. So here, this bar denotes the conjugate, the complex conjugate. So okay, ring LWE. We first take the dual of the entire ring of integers. What is also nice and often used in practice that if the number field is monogenic, then the dual has this nice expression. We also define quotients of the dual modulo Q. And we have the property that essentially RQ is a proper subset of the dual of RQ. Let chi E be some distribution over a dual of R. And we define the ring LWE sample as follows. This is essentially a noisy product where A is taken from the ring RQ, S is taken from the dual RQ, and E is taken from the error distribution chi E. And as for LWE, we have two versions of this problem. We have search version, where we need to find S, and we have the decision version, which asks to distinguish between a uniformly random pair of elements from the dual and from RQ, and a proper ring LWE sample. So what is interesting, we don't have a general search to decision reduction for ring LWE. We only know how to do this for secatomic fields, namely to the fact that secatomic fields have very nice Galois group, and also we can find such a Q that RQ splits, that RQ essentially splits completely into direct product of a ring of integers modulo Q. It was proven by Lubashevsky, Packard, and Regev, and later that decision ring LWE is at least as hard as approximate a psi VP for any ideal lattice. But unlike for Cs, for ring Cs, the reduction is quantum. So we need to have quantum computer. So in this work, like the first result on hardness was established, but in this one, it was proven that essentially we don't need to go from decision ring LWE to search LWE first in order to prove the hardness. So it's sort of direct result where we go from decision ring LWE directly to hard lattice problems. So what are the advantages of ring LWE? As for Cs, we have a much more efficient problem because we can keep less data, and also we can perform operations using fast Fourier transform if our ring is nice enough. But we have drawbacks. First of all, that hardness of ring LWE is based on a specific family of lattice problems, and namely the hardness is based on ideal lattices. And ring LWE is less flexible for cryptographic constructions. So the question is whether there's some other problem right in between ring LWE and LWE, which sort of balances these advantages and drawbacks. And yes, it exists, and this problem is based on module lattices. So let's take some module M, our module, in the space k to the d. And if the ring of integers of k is a Dedekind domain, then M has a pseudo basis, which means that we can define the rank of M. And we assume the rank of M is maximal, so it's D. We'll also kind of extend the canonical embedding to this vector space k to the d, where essentially for every element of kd, for every coefficient of kd element, we compute his canonical embedding. And the image of this map the image of M under this map is essentially a module lattice. So in fact, these module lattices, they generalize ideal lattices, and they find their sweet spot between general lattices and ideal lattices. So between LWE problem and ring LWE problem. So how to build module LWE problem? It's super easy. Essentially, we take LWE problem and we replace all the elements by the elements of the dual of RQ, except for the matrix A. Here, it's enough to take elements. It's not enough. It's obligatory to take elements from RQ. And essentially, this matrix defines an R module M. So it was proven by Langlois and Stellet that a module LWE is at least as hard as approximate SIVP for any module lattice by quantum reduction. They also proved that we can define in the same manner the module CIS problem, and the module CIS problem is at least as hard as approximate SIVP for any module lattice, but by classical reduction. So using ring LWE and module LWE, we essentially can do almost everything that LWE can do, but more efficiently, because we can use ring structure to make operations faster. We can also reduce memory. There's also a very interesting specific variant of LWE called learning with rounding. So in LWE, in CIS, and also for LWR, we used linear systems of equations, which can be essentially represented by a bunch of inner products of rows of A, of the matrix A, and the secret vector S. So LWR is a variant of LWE where instead of adding some probabilistic error to these inner products, we add some deterministic error by rounding these values to some multiple of, to the nearest multiple of some small integer p, not small, smaller than q. So this can be done in this very, very simple way. And this is much more efficient because remember that in order to have sort of secure system based on LWE, we need to generate discrete Gaussian errors. And in practice, this is very, very hard problem. And this is essentially a bottleneck in efficiency of many schemes based on LWE. Here, this operation is quite simple because we essentially can cut certain lower bits of these inner products. So decision and search LWR can be defined in exactly the same way as for LWE, and these problems are also equivalent. By analogy, we can replace matrix A by some structured matrix and define ring LWR and module LWR. And we have also hardness results. So for large enough Q over P, remember that Q is a larger modulus, P the modulus to which we kind of round our samples. So we can prove that ring, module, or standard LWR is at least as hard as ring, module, or standard LWE. So, and then since LWE is at least as hard as certain lattice problems, we have a hardness statement from LWR as well. We can also define very, very simple pseudorandom function using LWR. Essentially, we sample L Gaussian distributed matrices, SIs, and some uniformly random A. And then for any seed X, we essentially pick some subset of these matrices SIs defined by X. So we do it here. We multiply all these matrices together, multiply them with A and around. And as a result, we'll get some pseudorandom output. So the security of this pseudorandom function, which relates to the fact that SI and A should be secret, the security of this pseudorandom function is based on LWR. In addition, we also can build public key encryption schemes based on LWER, but mainly because we have this deterministic error, we can't do that much as with LWE or ring LWE or module LWE. And the last but not least, untrue. This is actually a very old encryption system and cryptographic problem, which appeared around in the same year as iTie's hash function, and it's algebraic. So namely, we have again some ring of polynomials, but now modulo some reducible polynomial x to the n minus 1. We have a distribution chi-k, which samples elements of R with ternary coefficients in the power basis. And we have two integers q and p, which are co-prime, and p is much smaller than q. Then search and true problem is defined in the following way. We sample two polynomials f and g, two elements of R, from this distribution chi-k, and we check that f is invertible in RQ and in RP. And then we compute this H, and the goal is to find F and G from this H. We can also define the decision version of untrue. So essentially, we need to distinguish between H and some uniformly random element in RQ. Untrue was published not as a problem first, but as an encryption scheme. And this encryption scheme is called untrue encrypt. So it's quite obvious that Alice essentially generates these polynomials f and g. F must be invertible modulo q, but also modulo p. So I forgot to put rp here. And the public key is the ratio modulo q. So this is a public key, and then Bob uses this public key, also samples some element R with ternary coefficients, multiply it with H, multiply it with integer P, and adds his message. And what is important, this message can be any polynomial with binary coefficients. And then Alice, having this encrypted message C, can compute the following expression, which yields the message. So essentially, in order to extract any information from H about F and G, we need to solve search and true problem. And as well as here for C, C also looks uniformly random due to decision and true problem. Untrue can be represented as a lattice problem, apparently, because this ratio H defines a lattice, namely module lattice, defined by H and 1. And it looks very much like a cis instance over RQ, or if we expand this as a matrix vector product and J as a vector over Z, then we have an instance of cis over Z. Then, in order to solve untrue, we essentially need to find a short vector in this lattice, defined by one H, or by these metrics, where this matrix AH is a matrix of multiplication by polynomial H in RQ. But there's no reduction in an opposite direction from worst case lattice problems to untrue. So essentially, we only can rely on more than 20 years of very extensive analysis about this problem. And also untrue had some interesting attacks which exploited the structure of polynomial ring. But however, we can change untrue encrypt system such that it becomes semantically secure, namely that encrypted messages of this scheme looks uniformly random. What essentially was done by Stille and Steinfeld in 2011, they reformulated untrue as ring LWE. So they introduced additional distribution chi-e, and together with the distribution chi-k, these are discrete Gaussian distributions with wide enough standard deviation. They also changed the ring R, taking 2 power cyclotomic to nth cyclotomic polynomial, and they changed the encryption function by adding the noise which was sampled from the error distribution chi-e. So essentially, to distinguish C from uniformly random value, one should be able to solve Pringle-Wee problem. So using Entru, we can design public key encryption schemes. We can design signatures. This is pretty standard. But we could also do pretty interesting stuff as fully homomorphic encryption or cryptographic multilinear maps. In cryptography, multilinear maps are essentially interesting when they're defined over the groups with hard discrete logarithm problem, roughly speaking. But the problem is that all these crypto systems were broken because in both applications, Entru need to have super polynomial modulus Q, and there exists a sub-exponential attack on such Entru instances. And this attack is classical. So in the conclusion, are the problems I presented going to be practical? The answer is yes, and currently the US National Institute of Standardization assesses various cryptographic algorithms that are hard even on quantum computers. So these algorithms will replace in the future the classical crypto such as RSA or ECC that we use now. And in the current round, round 2, 12 out of 26 submissions are based on lattices. So lattices are definitely a hot topic now and in the future of cryptography. So thank you, and I would like to thank especially the organizers for their amazing work.